In this video, I'm going to talk about the nonlinear shooting method, extending on from the previous video on the linear shooting method. So, in the notebook, we want to think about a few things here. Why is it called nonlinear? It's because it's for nonlinear differential equations. It's actually one of the only times we really introduce nonlinear form of solution to nonlinear differential equations in this course. The nonlinear shooting method, I think of it quite in a simple term of Angry Birds, because you take a guess, you see if you hit the answer you know, and if you don't, you do it again, and every time you make a more and more educated guess. So let's talk about it in general terms. In general terms, what we have is a nonlinear second order boundary value problem. Y double dash equals some function of x, y, and y dash between the points a and b. We're given the boundary at a and we're given the boundary at b. So that's everything we're given. Like with the linear case, we divide this into two second order initial value problems. Identical to the linear case, the first second order initial problem is the same as the one we had, except we have a new initial condition. Unlike the linear case, this lambda 0 is a guess. This lambda 0 is our initial direction, our initial angle almost, you think of it. It's the initial velocity of the movement. Now, the second equation is a bit more subtle. Because we've introduced a new parameter, lambda, that we have actually we have two dimensions here. We have x and lambda. So we have to introduce a new variable that y is a function of x and lambda. So we can differentiate everything with respect to lambda. That gives us a new term z. So z is dy d lambda. So it's kind of a funny thing. To solve a single variable problem, we're adding in an extra variable such that we can span a new space. So our new equation is z, the second derivative of z. So what we're actually doing here is we're taking the boundary value problem and differentiating with respect to lambda. So we have z double dash, which is dy squared lambda, or the second derivative with respect to x, and then with respect to lambda. Df dy dash. The reason why we have that is because we're differentiating z with respect to lambda, but z is a function of x, y, and lambda, and y is a function of both, so we have that. And then we differentiate just with respect to y, and that gives us z lambda. So now we have df dy dash and df dy, and then we have z and z dash. So these terms here are what we have to calculate for every single version of it. Like the linear method though, we have za is equal to 0 and z dash a is equal to 1. So that stays consistent. So unlike in the previous case, actually y1 is our answer. We don't have to do some linear sum. What we're doing is trying to refine our estimate of lambda such that it actually gets us to beta. It gets us our yb. So we have to introduce an iterative process of guessing your lambda, and we use a form of Newton-Raphson. So we have to solve all our equations and then update our lambda. The objective is that our previous lambda and the current lambda should be as close as possible. And so here's just the Newton-Raphson is yb lambda k. So yb is actually the answer we have, or yb1 is solution we have. yb1. So what we actually want to solve each time is get a new lambda, and in the end, if the lambda you have and the new lambda are very close to each other, that means that y1b minus y1b is very similar to beta. So therefore, actually, we've hit the point we want. We keep updating. So here is our criteria. We have to keep updating lambda until the lambda we have, the lambda we now iterate to, are close to each other by some tolerance. So as I say, the introduction of lambda is the introduction of a new variable that motivates the second order initial value problem. So here we are with a simple example. So here we have our shooting method for y double dash is equal to minus 2y y dash. Yeah. Our boundary value problem is broken up to 2 second order initial value problems. Our first problem is very straightforward. U double dash is equal to minus 2u dash. Yeah. We have our initial condition that we're given, and then we have our guess one. Yeah. So now we can rewrite that as two initial value problems. Y dash 1 is equal to u2. Y dash 2 is equal to minus 2u1 u2. Y dash 2 is equal to lambda 0. Now the second one is we have this new term z. Now we never really have to refer to z ever again as dy d lambda, but that's what it is. It is dy d lambda. It's looking at how y changes the function of lambda. But to calculate that, we have to differentiate the original equation with respect to y and then with respect to y dash. Yeah. So what does that give us? That gives z double dash is equal to minus 2y dash, because that's the derivative with respect to y. And minus 2y dash, 2y z dash is derivative with respect to y dash. Very straightforward. And it does look very similar to the original, but you know, we have the separation. Z is equal to 0, z dash is equal to 1. Z dash 0 is equal to 1. Now, what we have here though is this new equation has y's in it. So when we discretize it, we actually have to use the solution from the previous differential equation in our new initial value problem. So that means we have to solve everything together at the same time. And we have to do one full iteration of that. And then we get our new lambda. So here I choose a guess of lambda naught is equal to 0.2. How to choose lambda naught? I'm sure there are a couple of educated guesses. You can go, okay, well, since y naught is minus 2.5 and y1 is 3, therefore it must be increasing. So let's have a positive derivative. That's not a bad place to start. Probably you could do something like 3 minus 2.5 divided by 1. So you could even start with 7.5, 5.5, a positive number. It doesn't really matter where you start. Okay. And we will run this for as many iterations as possible until the two lambdas are of a tolerance of 10 to the minus 3. As before, as always, we discretize our domain. And now these are initial conditions. y10 is equal to minus 2.5. y20 is equal to lambda 0. z0 is equal to 0. z20 is equal to 1. Beta, which is our endpoint that we're trying to get to, is equal to 3. And I estimate lambda naught is equal to 0.2. Yeah. Here we are just stating those facts. So, in our discrete form using our Euler method, we have y1 I plus 1 is equal to u1 I plus 1 is equal to u1i plus h u2i. u2 I plus 1 is equal to u2i plus h times minus 2u1 u2. And once again, u1 naught is equal to minus 2.5, u2 naught is equal to lambda 0, which is 0.2 in this case. Z naught is equal to z1 plus h times z2. z2 I plus 1 is equal to z2i plus h times 2 z2i, yi minus 2 z1 y2i. Okay. And at each iteration at the end, we know that the approximate u1i is the approximate of yxi. That's actually our answer. This is to get to our answer. That's our answer. So we have our initial choice, 0.2. We need to find out what u1 at the last point, which is 10, because we have 10 steps, and z1 at the last point is. Okay. Now, here we have our loop. We have our tolerance. K is our iterative loop. I have an option between K is 10 or K ends. Either is acceptable. So I have a break if it goes longer than that. And so what we have here is our first loop. This solves the first second order initial value problem, which is divided into two first order initial value problems. This is for our second order initial value problem. Now, what I have to emphasize here is you see here they have to be contained within the same loop, and they're outside this while loop. So we have this, we solve, we update our lambda, and then we go again. We change the value of u2 to be this new lambda. So this derivative gets taken in. And so what we have here is for every single step for the approximation, for the first lambda, for the second lambda, for the third lambda, and as it keeps on going up further and further, you see it gets closer and closer because the exact answer is x equal to 1, y is equal to 3. And it gets closer and closer to that. And you see between the 4th, 5th, and 6th, they're almost identical to each other. Yeah. This is our final answer, which is for lambda is equal to 6. That is our solution. Here are different iterative values for lambda, starting at 0.2, going up, and plateauing at 1.4. The value of lambda is what we're using to stop our criteria because that's actually the right value. So I'm going to rerun this code very quickly, one time with a slightly different lambda. I'm going to choose a lambda is equal to 5.5 because that's starting above. So that's, restart and run all. It started very high, it goes lower, and then once again it plateaus around the same value. Yeah, it took 9 iterations in this case. The first iteration, you see, it went down. Second iteration started plateauing up. Third, fourth, fifth, all the way to the right answer. Now, the lambda is always the same because the lambda is the velocity at that point. That's what you're kind of estimating. So let's say instead, if we take a bad initial value, well, not a bad one, but a different one, let's say minus 5.5. This probably won't converge within the 10 trials. You see here, it's not getting anywhere close. Oh, but at the beginning it's nowhere close, but actually by the end, let's have a look. It's a terrible answer. Getting nowhere near our value. But it is slowly increasing up towards it. So let me run it for, instead of stopping at 10, let's stop at 20. Or reaching the criteria. Oh, so you see here with a terrible initial value, it's actually resetting itself and can't get to it. So while it's tending up, it can't flip over that line for some reason. So the initial choice has to be a reasonable initial choice.